Okay, so now let's take a look at a few examples for how we can apply these equations we were just talked about in the previous lecture segment. And let's start off with a single phase example where what I'm doing is I'm supplying a motor load. And so the scenario looks something like this, where this is a single phase circuit. I've got a transformer that's supplying a motor. It's supplying it between X1 and X3. So basically this is going to correspond to 240 volts. And then I've got a connection to my source through an overhead line, which is just going to be single phase. And so I have a phase conductor, I got a neutral, and then I'm bonded to earth at the transformer side. And so some of this current could actually flow through this earth plane. So I've got a 10-mile circuit in this case. And so for the parameter values, I've got a motor that's consuming 20 kVA at a power factor of 0.98 lagging. It's operating at a rated voltage 240 volts. I'm going to work backwards and figure out what's going to be the required primary side voltage at the source. So the transformer is 25 kVA. It's got percent resistance and reactance of 1.2%. And then for the overhead, I'm going to have a 1/0 ACSR conductor for both the primary and the neutral wire. The distance between the two is 4 feet. GMR for that wire is 0.00446 feet, and the resistance is 1.12 ohms per mile. Ground resistivity is 100 ohms meter, which we're going to use for the Carson's correction calculation. So again, what I want to do is I want to work backwards, figure out the source voltage. And then the other thing I want to do is I want to figure out how much of that current is flowing through the overhead neutral wire versus the earth return. So first of all, what we need to do is we need to get everything on a consistent system, right? A couple different ways we could work this. One, if I've got the transformer value in per unit, what I could do is I could convert the line impedances into per unit. That'd be one way I could work that. The way I'm going to work it here, though, is I'm going to take the load, I'm going to refer that to the high side of the transformer, and then also I'm going to convert the transformer impedances to the primary voltage side. So I'm going to work this in terms of ohms and amps. This is typically the way we'd work problems like in a power flow, is we typically work things in ohms and amps in terms of per unit. So even if I had a transformer value in per unit, the program would actually convert that to set of impedances in ohms. So in order to do that, I'm going to get everything on the 7200 volt side of the circuit. So basically, I got a 7200 volt nominal source. What I'm going to do is I'm going to get everything worked on this side of the circuit. This is the 7200 volt side. And to do that, then I'm going to need to have the base impedance. So the base impedance is voltage squared over the power rating. V squared over 25 kVA is 2073 ohms. And so I would take the resistance in per unit multiplied by the base. And these are in terms of actual ohms. And again, this is on the 7200 volt side of that transformer. So I'm referring all the transformer impedances to that side. Now for the load, if I'm operating at 240 volts on the primary side of the transformer, it's almost at that load where it's 7200. So if I take that load power, take the complex conjugate of the arc cosine of the power factor, that gives me the angle for the current. If it's a lagging power factor load, the current needs to lag the voltage. I'm going to go ahead, and if it's not shown here, I'm going to use just 0 degrees for the voltage as a reference at the load. And then what this enables me to do is to get this current on the 7200 volt side. All right. So instead of calculating this on the 240 volt side and using the turns ratio, I'm just directly getting the current as seen on the 7200 volt side for the load. And then for my line model, I need to calculate D sub E. So I plug in 100 ohm meters here, and this gives me 2788.5. I'm not sure if I get that units on there exactly correct, but and then what I'm going to do in here is I'm going to go ahead and then use my formulas for calculating the impedances. And note these are going to be the prime values before I do the Cron reduction. So since I have the same size wire for both A and N, I got ZA prime, which is the same as ZN primed. You take the actual wire resistance, add to that the resistance, and to get the reactive part of that, the imaginary part of that, I should say, that's going to be J.1213 times the natural log of DE over the GMR. DE is 27.88, 2788.5. GMR is 0.00446 feet. Make sure that when you're working on this, the numerator and denominator have the right units. I did have the right units on D sub E. I did have that in feet like I needed. Because I had the GMR value in terms of feet. So I have to make sure the units match. I'm adding the Carson's correction resistance for getting ZA primed and ZN primed. And this gives me the self-impedance terms on a per mile basis. For ZAN primed, I just simply take the resistance associated with the earth return, add to that J.1213 times the natural log of DE over DAN, where DAN is the distance between the phase conductor and the neutral. And so this gives me the off diagonal term. And what I need to do is I need to just simply get this in terms of one impedance for the A phase wire. And to do that, I need to apply the Cron reduction. And so before this would have been a 2x2. And if I apply the Cron reduction, I just get this particular term. And this gives me the equivalent phase impedance. So now all I need to do is I need to basically sum up the net Z associated with the overhead line and the transformer. I need to take this line impedance per unit length. I need to multiply by the total length of the line, which is 10 miles. I add to that the transformer impedance. I multiply this by the net current going through that line and transformer in series. I add to that the voltage I would have across the load. If I take the 240 volts, refer to the 7200 volt side, that gives me 7200. And this gives me a source voltage of 7342 plus J49. And if you take the magnitude of this, is 7342. One thing you'll note in this case is that this imaginary part of the voltage is very small. It's basically negligible in this case. And so anyway, I basically worked from the load over to the source, and you can see that the voltage drop magnitude is about 142 volts in this case. So the next thing would be, well, once you've got this current, then how much of this current goes to the neutral wire and how much of this current goes to the earth return? And the way you would have to calculate that is you got to go back to this 2x2 relationship. And we basically told you before that we assume that this term here is equal to 0. And so if this term is equal to 0, then what you can do is if you actually had this expression, now you can figure out what this is. And so you see that IN primed is minus ZNA prime divided by ZNN prime times IA primed. And basically it's kind of like a current divider in a way, if you want to think about it. And basically what this says is the actual neutral current magnitude is going to be 1.098. And so if you took the difference between these two currents, then that would also give you the current going through the earth return. And so it's a split effect right here. You know, some of the current goes to the neutral wire, some of the current goes to the earth. And it kind of depends on the relative impedance relationships between the neutral wire and the earth return. All right, so for three-phase, let's suppose we had a situation where we had a construction that looks like this. I kept this kind of simple. Basically, I've got 3 conductors that are on a cross arm, 3 feet between A and B, 4 feet between B and C. The neutral wire is kind of dropped right below, kind of below B in a way, where this offset you can see right here is actually 4 feet in this direction and 3 feet from the right. And then the neutral conductor is going to be 25 feet above the ground. And so I've got all these different distances, and what I can do is I can then use this information to calculate the different distances between the phase A, B, and C in the neutral conductor. And so what you're going to end up with is, in this case, you have this sort of combination of different conductor to conductor resistances. We'll assume that we have a phase conductor wire that has a resistance of 0.306 ohms per mile. The GMR is 0.0244 feet. And we'll have a smaller neutral wire with a resistance of 0.592 ohms per mile and a GMR of 0.00814. So what you see is a neutral wire in this case is actually smaller than the phase. Now, why do we do this? Well, it turns out that the load is somewhat balanced, that the neutral return current should be smaller than the phase A, B, and C currents. In other words, there's going to be some cancellation, so there's not, under balanced conditions, not as much current flowing back through the neutral. And so for that reason, we don't usually put up a neutral wire that's as large as the phase conductors. We usually have a smaller wire up there. And so we'll assume that we have earth grounding in this case, 100 ohm meters for the resistivity terms. DE again is going to be 2788.5. 100 ohm meters is a very standard number we would use. And just, for sake of reference, we got 336 conductor for the phase and a 4-aught conductor for the neutral. And so normally the neutral wire is usually like 1 step lower in size than like the phase conductors. So what we're going to do is we're going to use the formulas for coming up with the impedance matrix in this case. So we want to calculate the impedances per unit length. And we have this formula for the diagonal terms, and we have this formula for the off-diagonal terms we're going to apply. And so we're going to calculate this 4x4 matrix relationship using these formulas, which are take into account the wire resistance, D sub E, the GMR, takes into account the earth return effect as well, plus the distance between the wires. These are just some sample calculations for a couple of terms in here. And what you'll note is that the off-diagonal terms, these are all the off-diagonal terms in this case. The off-diagonal terms will have different imaginary parts because of the difference in the spacings, all right? The other thing we'll see is for the neutral wire, we've got a different self-impedance in the phase conductors. And so what we need to do once we have this 4x4 is you need to do the Krone reduction, where basically we're reducing out the 4th row and the 4th column and getting us back to a 3x3. So this just shows a couple sample calculations for ZAA and ZAB where we're doing the Krone reduction. And this gives us the final form, which is a 3x3 that we'd use, say, like in a power flow program. So we're still modeling, even though we don't have the neutral in there, we don't have the earth conductor in there, we're still modeling those effects as far as calculating the phase A, B, and C voltage drops. So again, you'll see that the diagonal terms are not exactly the same, and the off-diagonal terms are going to be a little bit different because this is not transposed. We're not moving the conductors back and forth like we would in transmission. This is not transposed in this case. If we wanted to model transposition, then one way we could do this is we can just simply take an average of the diagonal terms and the off diagonal terms. And so if we wanted to calculate like a value of z sub s and zm, and we wanted to do this in terms of like get symmetrical component sort of values, we could do this. But what we would have to do is we would have to have balanced situations, and we get that by assuming transposition. So if you assume transposition, basically that's the same as taking the average of the off diagonals, taking the average of the diagonals, and this would give you ZS, this would give us ZM, and the positive sequence impedance is ZS minus ZM. So this is going to be 0.306 plus J, 0.63 ohms per mile. And this is what we would use for balanced per phase analysis. So later on, when we do some K-factor calculations, which we'll be doing for homeworks, we assume everything's balanced. This is where those values would come from. If we do per phase circuit analysis, what you're doing this based on these positive sequence values. Now, you could also do these calculations in windmill. And so this shows the same example where I've taken the circuit. What I've done in this particular case is, instead of modeling this exactly the same, I was more interested in just showing you the impedances in this case. So what I've done in here is I've just created a situation where you had 1 mile of the same sort of overhead line, just to show you how MillSoft would calculate these same values right here. And so when you set this up in MillSoft and you have an overhead in there, and I'll post this up on the Moodle site, what you would do is you would set this up where in your overhead model, then you'd put in the phase conductor, and then you put in the neutral conductor. And what you can do is you can make phases B and C the same as phase A. That would kind of make sense. You make all phases the same. And what you're doing is you're linking in an equipment database through these little push button interfaces right here. You can actually tie this into an equipment database that has these conductor values loaded in. The spacing would be stored in this construction equipment entry. And note, I'm just setting this up for 1 mile, 5,280 feet. So if you click on the equipment link that shows you the equipment information, note what I have in here is I've got a resistance in here that kind of matches up to what I want to use. I'm assuming that this is going to be a 50-degree C value. I don't think it shows here, but I'm assuming this is a 50-degree C value. So I've got this set up to use 50-degree C. I've got the GMR plugged in. I'm not using the diameter for anything right now. You can put in the capacity of the wire, and you have a similar entry for the 1/0. And then for the construction, then you have another database for that. And then you could actually put in the distances between the wires. And so, for example, I'm assuming as my reference point, kind of like the bottom of the ground at the bottom of the pole, I'm using my A phase as like the X reference. And so what this means is that the A phase conductor is at 0 feet, 29 feet above ground. B is located 3 feet over, 29 feet above ground. C is located 7 feet over from A, 29 feet above ground. And then the neutral is 4 feet from phase A, 25 feet above ground. And then what Windmill does is gives you a little bit of drawing here to tell you that you got this set up right. Note, one thing you have to watch out for is make sure you get the right units in here. And so sometimes I think that defaults to inches. And so if you're putting in feet, make sure you have this set up for feet right here. One thing on here you can also have is you can click on whether you want to assume transposition. And if you were going to click on this little box here, what it's going to do is going to transpose the line elements. Otherwise, it's going to keep it unbalanced. So now when I do this, you'll note what I'm calculating now is I'm calculating this 3x3 impedance matrix. And since I set my line length up for 1 mile, then basically what this is, it turns out to be a 1 mile value. And you can see that it does match up with what I had in my equations from my equation analysis right in here. All these values match up because what Windmill is doing is using the same equations as I just showed you. Okay, now if you do the voltage drop analysis now, then for this little circuit right here, what you can do is you can run a power flow study. I put a certain amount of load in there, and what you can see from this is you can see your voltages and you can see your currents. And you'll note in here that these voltages do not have the same magnitude now. Because of the imbalance in the impedance matrix, the current flows are going to result in different voltage drops per phase. And so you're going to get a slightly different set of currents in here because we have a constant power model. If the voltages are imbalanced, the currents get imbalanced. And what we get out of here is we basically see that we don't have a balanced set of voltages and currents anymore. Even though the load itself was balanced and the transformer was, say, like 3-phase imbalanced, the fact that I have a transmission or a feeder model in there, an overhead model in there where I don't have the same distances between phases, is going to give me different voltage drops per phase, and it's going to give me slightly different currents. All right. So it's not just load imbalance that causes imbalanced voltage. It's a fact we would have untransposed overhead lines in our system. Now, what you could do if you wanted to assume transposition, there's a couple different ways you can do this. Another way you can do this, if you go into Analysis Manager, what you can do is you could check assume transposition. And now when you run voltage drop, it updates the impedances, and look what's going on with the impedances now. All the off-diagonal terms are all the same, all right? 0.156 plus J, 0.433, they're all the same now, okay? So all those mutual terms are all the same. So this is the effect of having the transposition. And now when you rerun the power flow, basically what you see is now all these voltages on phases A, B, and C are the same. And so we've gone from an unbalanced situation to a balanced situation by assuming that we have transposition. Transposition is really not used out in the field that much for distribution. It's more of a transmission thing. You may have the conductors kind of get swapped around as you take corners and stuff on your primary, and sometimes the phase positions get swapped around. But you typically don't intentionally do this for doing balancing. And so this is kind of an inherent thing that we're going to see for distribution as we get imbalanced voltages because of the fact there's unequal distances between the phases. All right, so anyway, if you want to read on this some more, you might want to look at my notes, or you can look at the Kirsting book. They're kind of similar, but he's got a section, chapter 4.1 on series impedance of overhead lines, which we just did. And so what we'll do next time is we'll take a look at cable impedances. We'll go through a similar set of steps, and we'll show you how you can calculate these impedances for the cables. And then one last thing is that if you're interested, as far as a lot of guidelines on distribution circuits, a lot of these can be found at this U.S. Department of Agricultural site, USDA Rural Development, and they have all these different guides. It has drawings and a lot of good factual information on how to do distribution. So this might be a good reference for you guys in the future, because typically utilities won't publish this stuff. For those, keep that internal, where these set of guidelines are public. All right. So that's all I got for this, and then the next lecture we'll get into the cable modeling then.